Okay, hopefully you can hear me now. And we saw the same movie as we saw yesterday, where you can see that there was the inflaton field producing a different field within order 10 oscillations or less. Here is the movie going again. And you can see, right, that the first field that gets excited is this field chi within a very few oscillations of the inflaton. And then we see that the fact that chi is excited, there is a phenomenon of rescattering, where the field chi scatters against the inflaton, and eventually both fields get fragmented. And we see that we are left with a populated state that is essentially completely not homogeneous, right? So you see homogeneity of the inflaton has been destroyed. Now we can stop the movie, and I'm going to share one slide that I prepared. So here is what we're going to do now, essentially. This is taken from Kaufman-Linde-Starobinsky paper, that there is the growth of the field excitation chi, and on the bottom, there will be an associated growth in the particle production, in the number density of the field chi. So what we're going to do now in this lecture is to properly define the occupation number and then to compute its evolution. So that's what we're going to do right now. So let me now go back to the board. Okay. So I will start essentially with, that's the goal. First, we're going to do review of QFT quantization of a free field. Actually, we're going to take a free scalar field, the simplest possibility, and then we're going to do a quantization with a time-dependent mass. I will show to you that the phenomenon we just described for the field chi can be understood as just a problem of quantization of a free field that has a time-dependent mass. And this will generate excitations of the field itself. But the first thing I'm going to do is something very textbook. So I apologize for those of you who know these things very well. I assume that many of you have seen this in a class. But nonetheless, I would like to bring everyone on the same page. And also, I would like to present things in a way that will make then the time-dependent mass calculation to follow naturally. So I'm going to just give things that should be known, or at least I think many of you have seen. First of all, we're going to use now Minkowski spacetime. So G mu nu is eta mu nu, which is, I'm going to use the signature starting with the plus. Then we are going to look this Lagrangian. So L is equal a half d mu phi minus a half m squared phi squared. So you see now m is constant. So the simplest possibility, right? Free field. And from the Lagrangian, we have the Euler-Lagrange equation. Which is d mu phi plus m squared phi is equal to 0. And then we define the conjugate momentum. So pi is dl d phi dot, which is phi dot, right? And you know, quantization is done, the canonical quantization, by imposing commutators, right? Phi of tx, pi of ty is I delta x minus y. And just to set notation, that's how I do my Fourier transform. Phi is equal d3k 2 pi 3/2 e to the I k dot x phi k of t plus phi minus k dagger of t. Notice the choice, phi of k, phi minus k dagger. The reason is because the field is real, right? So phi dagger is equal phi. And that's what forces me to take this minus sign. Now, why do we do Fourier transform? Because in a sense, the spatial derivatives, right, that you can see in this equation here, when you do the Fourier transform, they just become multiplication by the momentum. So the spatial derivatives just become algebraic terms, and we end up having only time in our differential equations. And in fact, if I write the equations in terms of the field phi and pi in Fourier space, that's simply what I get. Phi dot k is equal pi k, and pi dot k plus k squared plus m squared, phi k is equal 0. And this is the same equations of motion than the simple harmonic oscillator, right? So this is the same equation of motion, the simple harmonic oscillator that has a square frequency, kappa squared plus m squared. So the momentum and the mass, they both contribute to the frequency of this effective simple harmonic oscillator. So each mode, each Fourier mode, is a simple harmonic oscillator that does not talk with the other modes because we are doing linear theory, as you saw. And so we quantize in terms of rising and lowering operators. As we know, right, simple harmonic oscillator is one of the few cases that we know how to quantize exactly. And in particular, that's what we write, phi k of t plus phi minus k dagger of t is equal 1 over 2 omega e to the minus I omega t a k dagger plus e to the I omega t a k dagger, where these operators satisfy the algebra of the rising and lowering operators. And in the context of quantum field theory, this creates a particle with momentum p, and this destroys a particle with momentum p, with momentum k. Okay? When you do this, you can indeed verify. So you just do the Fourier transform, you write this, and you can indeed verify that you achieve this commutator here, which is the goal of quantization. So there is a full consistency between the algebra of the simple harmonic oscillator and the canonical quantization relations that we want to impose. So let's assume that we have verified all these. Then what do we do? Well, we compute the Hamiltonian. So the Hamiltonian is given by d3x pi phi dot minus L, which of course, if you take the Lagrangian of before, is d3x pi square plus di phi square plus m square phi square, right? So this is the pi square term, which is essentially the kinetic energy, gradient energy, and mass energy. Now what you do, you put all the Fourier decomposition here. I wrote the Fourier decomposition for phi, but you do the same Fourier decomposition for the field pi. And then you write them down, and notice that you write them in terms of the annihilation creation operators that we saw before. There is a long algebra that I'm not going to write here. And we get the result, a half d3k omega k, ak dagger, plus ak dagger, ak. So this is the Hamiltonian that we do. And then what we're going to do, we are going to do the normal ordering term. Normal ordering essentially removes the energy of the vacuum. And what we do here, essentially, we just means put the dagger terms before. So this switches, and this becomes equal to this, removing this half term. So d3k, omega k, ak dagger, ak. Finally, you define your vacuum in such a way that it is annihilated by the annihilation operator. So this is a definition, if you wish, of your vacuum state. And notice now, from the Hamiltonian, we have a very simple interpretation. This is the sum over all possible states. Since this is a scalar field, of course, we don't need to sum over polarizations. We don't have sum over spin. We just do the sum over all possible states. And this omega k is the energy of that state. And here you could imagine making a discrete sum if you put it on a lattice. And each state will have the energy. Remember, omega k is equal k squared plus m squared. So it's a collection of infinite number of simple harmonic oscillators. Each of them has its own energy. And this counts. So this we define it n hat k. This counts how many particles there are in that state. So you see that essentially, to define the occupation number, we are going to go through the Hamiltonian and through essentially this exercise where you have this very simple interpretation. You sum over all possible states, you multiply the energy of that state, and you count how many particles you have in that state. For example, I think it's pretty clear that if you compute the vacuum energy, how many particles there are in the vacuum, there is this number operator that is acting on the vacuum state, right? So here is pretty clear that we're going to get 0. So, but let me just do it simply. How many particles are present in the vacuum? Well, we use the counting operator. So this is expectation value of the counting operator in the vacuum. We are going to see, right, this is 0, A, K, 0. But then, as we saw, this is the definition of the vacuum, is the one that is annihilated by AK, so we get 0. So you see, consistently, the vacuum has no energy. Of course, if we hadn't done the normal ordering, this would not be the case, right? Because this term here, you see, gives energy for the vacuum. But you know, this is a prescription to remove the would be infinite amount of energy, right? Because each mode would have an energy. When you take this integral, you would get infinite. But this is a way that we regularize it. So now, essentially, I am done with the quantization in Minkowski, right? I'm assuming that many of us have seen already this, so I don't want to be too long. But now all the concepts that I've developed, we need to think how we do them if the mass depends on time. This is something that maybe very few of us have seen it before. And, but you see, it's very interesting because there is a very clear prescription, a very clear procedure. And now we need to adapt this procedure to the case in which the mass depends on time. As we're going to see, some of these things will need to change, and we need to see what they change, essentially. But before that, let me also understand why I'm interested in a system where there is a time-dependent mass. What does it have to do with inflation and reheating, in a sense? So let me now discuss the system, the Lagrangian, for the field chi and phi. So now we take the same model as before, in a sense, but we add 2 ingredients. So the expanding universe and the coupling with the inflaton. And we want to see now what changes, right? So let me first of all write the Lagrangian, the action for the field chi. This is equal a half d for x minus g mu nu, d mu chi minus g square, phi square, chi square. Now, I'm sorry for changing notation. Before we were quantizing the field phi in Minkowski. Now the field to be quantized is the field chi. So that's actually the terms of the actions that only depend on chi. There's going to also be the action of the inflaton, right? The kinetic energy of the inflaton and the potential of the inflaton. But here I'm only interested in the field chi. And for the purpose of this calculation, we are going to take the inflaton only to depend on time. As we saw right in the simulation, initially the inflaton was homogeneous, and the time dependence of the inflaton was exciting the field chi. Later on, the field chi makes the inflaton non-homogeneous, and therefore this calculation here will not be applicable any longer. But this is the phenomenon of rescattering. So what we're going to do now cannot account for rescattering, but it can account for the growth of the field chi. For this reason, for studying this, we are going to treat this as a function of time only. And moreover, the metric that we are going to take is the conformal metric, essentially. This is the one, also Massimo, you introduced it with the conformal time, right? And this case here, also we don't take perturbations of the metric, right? We take the metric to be a background homogeneous metric. So you see that there is this external function of time and this external function of time. Now, I wonder if there are questions.
Hi, thanks. I might have missed this, but are we making any assumptions about the field chi?
Well, what we are saying is that the field chi is a free field apart from the interaction of the inflaton field, right? In principle, the field chi could have self-interactions or could interact with gauge fields. It could have many other interactions. Here I'm saying two things, that the field chi is a scalar, and secondly, that interacts with the inflaton through this term. That's all assumptions I'm doing with the field chi.
Got it. Okay, thank you.
Sure, sure. Okay, so we have one function of time here and another function of time here. This is the new thing with respect to the Minkowski calculation that we did up to a moment ago. Okay, so let's take this. Let's write down the action. You see this is going to write as a half d for x. A to the 4 is the square root of the determinant of the metric. Here there is the inverse metric, a to the minus 2. And then we have d0 chi minus di chi minus g squared phi squared chi squared, right? Now you see that I want to get rid of this scale factor from the kinetic term. So I'm going to redefine chi goes in chi tilde divided by a, and so phi goes in phi tilde divided by a. So if I do this rescaling, what I will get S chi is equal a half d for x. I will get chi tilde dot minus a dot over a chi tilde, inside the parentheses, chi tilde squared minus di chi tilde minus g squared phi tilde squared chi tilde squared. Things would be almost trivial if A didn't depend on time, right? If A didn't depend on time, through this rescaling, I would absorb A away. But notice that A depends on time. So when I'm taking the derivative of phi, there's going to be a term of chi, There's going to be a term which has the derivative of chi twiddle, but there's also going to be a term that has the derivative of A, which is the one that we see here. Now, I want to simplify this a little bit, because you see, let me spell out this term here. So let me just look at the first term there. The first term there is made of 3 terms, right? So we are gonna get, well, let me forget about this half for a moment. K dot square minus twice A dot over A, chi twiddle dot, minus plus A dot square over A square, K twiddle square, right? So what I have done this square, the mixed product, and this square. And this term, I'm going to integrate by parts. You can see that this term can also be written as in this way. D in dt, this, right? This is exactly what we had before. And now I'm going to integrate by parts. And by integrating by parts, what I mean that this becomes a plus, and the derivative now acts on the left. Because notice I'm inside the integral, so I'm allowed to integrate by parts. So this gives me chi dot square, then there's going to be plus A dot dot over A, minus A dot square over A square. Chi, this is no longer dot because the dot has been put on the left, plus A dot square, A square, chi twiddle. And then you can see also that these terms and these terms simplify away, so that we end up only with a term with the second derivative. So let me now put it together. This term will be the one that is present here. So when I write everything together, that's what I end up with. S of chi is equal a half d for x. Then we will have chi twiddle dot square minus di chi twiddle minus g square phi twiddle square minus a dot dot over a times chi twiddle square. And now I can see that indeed I have a time-dependent mass. Because phi tilde is a function of time, and the scale factor A is also a function of time. And this plays the same role as the mass in the Minkowski calculation. But what is now different is that the mass depends on time. So again, I will go to Fourier space. You see, I'm now in my mind, I try to do the same steps that I was doing before. But now I will do the quantization in terms of the field chi tilde. Notice that it has kinetic terms that are standard, right? It has canonical kinetic terms, but there is the effect that the mass term now depends on time. And if I just look at the equation of motion in Fourier space, of course, this will be chi twiddle dot dot, now is in Fourier space, plus kappa square minus a dot dot over a plus g square phi tilde square of t chi x is equal to 0. This is omega square, right, of my simple harmonic oscillator. I have a frequency that depends on time. There are two terms that I can see here. This term here accounts for gravitational production. There are papers that study the excitation of a field just because the universe is expanding, even without coupling it to the inflaton. For example, I could study this model for g is equal to 0. And as you can see, there's going to be particle production just because the geometry is expanding. Every field experiences this. Is that in many cases it's a negligible effect, but in principle any field experiences the excitation because it doesn't live in Minkowski. And however, here there's also this possibility. This is the production from oscillating inflaton. So you can see that with the same formalism, we can account for both these two effects that are two different physical effects. If you want to make an analogy, you make the analogy with the pendulum with the changing length, right? That would be the analogy. So imagine you have the equation for the pendulum. And then what you have that, in a sense, it's an analogy with the pendulum. With a time evolving length. So imagine you have a pendulum, right? And during the oscillations, you change the length of the pendulum. Maybe you move it up and down. You can see that eventually you will excite excitation in the pendulum, which in our language corresponds to particle production. You could also imagine that if you have a pendulum and you change the length very, very, very slowly, the excitations will not take place. This is called adiabatic variation of the frequency of the pendulum, right? Any pendulum has its own natural frequency. By changing the length, we change the natural frequency. And we can imagine changing the length very quickly. Then, of course, the pendulum will get excited. This is the equivalent of particle production. Or you can imagine changing the length very, very slowly, adiabatically. This is going to be the equivalent of not having particle production. And if, for example, this could happen if the inflaton moved extremely slowly. Imagine that the inflaton always moves very, very slowly. It's true that this function changes with time, but in a negligible way. This does not create quanta of the field chi. Okay, so now let me go back now to do the calculation. When I look at the equations of motion, nothing changes if I write the equation of motion as before. So I will have chi tilde dot is equal pi k, and pi k dot is equal plus, well, that's how I wrote them before, kappa square plus mass effective square chi k is equal 0. Right, this is the mass square effective term. But if you just look at the system of equations, it doesn't really change. Also notice that the kinetic term is canonical, so the conjugate momentum is defined in the same way as before. So this doesn't really change. However, what it changes is the mode functions, because when you compute the mode functions, the fact that this depends on time doesn't allow us to have the same mode function solution as before. Before, the mode functions were e to the minus I omega t and e to the I omega t, where omega was a constant. But now if this is not constant, you can just check this is not anymore a solution of the equations of motion. And in fact, in order to study the equations of motion, to solve, the equation of motion look the same as before, but the mass depends on time. To solve them, it's convenient to change variables. And instead of having phi and pi, we define two new functions that are called a of k and beta of k that are called Bogoliubov coefficients. At this level, maybe you have heard the name. It's nothing really but just a change of variable. In particular, that's how we change the variable. X tilde, chi tilde, is a kappa 2 omega k plus beta kappa 2 omega k. And pi chi is equal minus I omega alpha kappa of t divided by 2 omega k plus I omega beta kappa of t divided by 2 omega k. So let me summarize. We have a Lagrangian that we were able to write as a Lagrangian in Minkowski space, because you see, effectively, we are able to write things as if we were in Minkowski space, plus a time-dependent mass. Then we do the same quantization as we have the same equations as before. Formally, they look identical as before, but the difference is that now the effective mass depends on time. We do the same Fourier decomposition as before. I'm not even writing it down because it's exactly the same as before. And if you remember, there is the function phi, and there is the function pi. Pi is the canonical conjugate of phi. Pi is equal phi dot. And there is the system of equation. We do the Fourier transform, but it's convenient for reasons will be clear maybe later in the discussion. You can solve the problem in terms of the variable phi and pi, or equivalently, you can solve the problem in terms of the variable alpha and beta. You see, this is a change of coordinates in a sense. From chi and pi, you go into alpha and beta. And so in a moment, I'm going to write the equation of motion for the system in terms of alpha and beta. Alpha and beta are also called Bogoliubov coefficients. Just a name. Is there questions?
Yes. So the question is, are we still considering a slow roll phase of inflation?
Absolutely not. In principle, anything is valid, right? Because you see, up to this moment, I didn't specify anything. I just say that there is a FLRW universe. So the universe is homogeneous isotropic, expanding universe. But I didn't tell you what is the function phi, right? So this could still be valid during inflation, where phi does a slow roll, or this could be also valid during reheating when phi is doing oscillations. At the moment, this is completely general formalism. Later, we will apply it to preheating, so to the oscillations of the inflaton field. But what I'm doing here doesn't say anything, right? Because you see, this is valid for whatever functional dependence of phi. So let me write down the equations of motion. So I take the equations of motion in terms of phi and pi. I go in Fourier space, and then I do this change of variables. And as I do this change of variables, what I will find that these are the equations of motion, which are alpha dot is equal minus I omega alpha plus omega dot divided by 2 omega beta kappa. And then beta kappa dot is equal I omega beta kappa plus omega dot divided by 2 omega alpha kappa. Where remember that omega is a k squared plus mass effective square. And remember that now the effective mass depends on time. So these are just the equations of motion written in terms of these new variables. Now, the standard case which is omega is equal constant, admits the solution alpha k is equal e to the minus I omega t, and beta k is equal 0. This is the standard QFT solution. In this case, we have the same solution as before, right? And this is the textbook case, because the textbook case is a particular case where there is a constant value of omega. But now, this is no longer a solution if omega is not constant. In particular, we can always take at the beginning beta is equal 0. In a moment, I will discuss with you what is the physical meaning of beta. I could start with beta is equal 0. But you see, the moment that omega depends on time, the presence of alpha generates beta. So if omega depends on time, I cannot keep beta is equal 0. And now we are going to discuss what is the physical meaning of this variable beta. So well, maybe we keep these equations for later use. So let's remember that omega dot different from 0 generates beta different from 0. To understand the physical meaning, we again compute the Hamiltonian. That's why before I stress so much the use of Hamiltonian. Now the Hamiltonian is more complicated because there is also the presence of the beta dependent term. And if I do the calculation, it's straightforward because you just go Fourier transform, and then you change variable into alpha and beta, and you just write down the Hamiltonian. It's a long calculation, but it's straightforward. And the result is the following. A half d3k alpha square plus beta square, which multiplies a dagger plus a dagger a. And then there is another term, plus 2 alpha k beta k, a dagger k, plus 2 alpha star, beta star, a k dagger, a k. And then there is omega k. The Hamiltonian is still real, as you can see. And notice that we recover the previous result in the standard case, remember? This was alpha is equal e to the minus omega t, and beta is equal 0. So you see that absolute value alpha is equal 1. And then we recover the same Hamiltonian that we had before, right? The Hamiltonian is equal d3k omega k divided by 2, ak dagger ak, plus ak dagger. So in the standard case, the textbook case, that's the Hamiltonian that we find, and we know exactly how to deal with this. But you see that now we are no longer in the standard case. Beta in general is different from 0. And when beta in general is different from 0, we end up with this more complicated Hamiltonian. And as I write it, I don't really understand what it's telling me, right? Because there are terms that I've never seen, and it's not immediate to me. How do I interpret this? However, things become more clear if I rearrange the Hamiltonian and I write it in matrix form. So let me take the same Hamiltonian and let me rewrite it in matrix form. So this is equal a half d3k omega k ak dagger ak alpha k star beta k star beta k alpha k beta k star beta k alpha k star ak hat dagger. This is just algebra, right? From going from the first expression to this expression, I just rewrote it in matrix form. But what I write here is completely equivalent to what I write here. However, when I write these into matrix form, something now clicks on me because I see that I can just redefine the annihilation creation operators. I'm just going to write this one as AK dagger. And as a consequence, this is exactly AK dagger. Sorry, the other way around. So actually, I am able to diagonalize the Hamiltonian. This is a half d3k omega k ak dagger ak plus ak dagger. So it's very interesting because now the Hamiltonian is still diagonal, but in terms of these new redefined annihilation and creation operators. So in the case in which beta is equal to 0, capital A is equal to lowercase a, right? So in the standard case, I'm not really doing anything. In the case in which beta is different from 0, I have a complicated Hamiltonian, but I notice that I can redefine the annihilation and creation operators, and I will have these new annihilation and creation operators, which are capital A, and I can verify that they also satisfy the algebra of annihilation and creation operators. It's just a matter of a quick check. So they are also legitimate annihilation creation operators, and they diagonalize the Hamiltonian. The Hamiltonian acquires the standard form when it is written in terms of these operators. But now I remember what I did before. I have defined the counting operator from the Hamiltonian. This is the diagonalized Hamiltonian, This is the one that I should use to count particles. So what I have, right? I just take the normal ordered Hamiltonian, which is done in terms of these fields here now. So this is D3K, omega K, AK dagger, AK. So I understand from the calculation that this is the counting operator. This counts the instantaneous number of particles that have that mass at that given time t. Now, we are doing this calculation in the Heisenberg picture, where operators evolve with time, but states do not evolve with time. And in particular, I choose initial conditions where alpha is equal 1 and beta is equal 0. And my vacuum is the one that is annihilated with A. Because you see, initially, at the initial time, so let me also rewrite these, well, let's keep in mind this change of variables. So at the initial time, alpha in is equal 1, beta in is equal 0. So the vacuum is still defined as before. The vacuum is the one that is annihilated by the lowercase a operator. And remember, we are working in Heisenberg picture. So the vacuum will always satisfy this property. The vacuum never changes. So this property will always be true, even at later times. But what changes is that the counting operator changes because this coefficient change. Right? Remember that alpha and beta satisfy the equation of motion. Therefore, alpha and beta depend on time. Therefore, the choice of the number counting operator depends on time. And so now I have all the ingredients to compute how many particles are present at the time t. So the total number of particles, the number of particles with momentum k presence at the time t is the vacuum, the counting operator, vacuum, which is vacuum, counting operator made of the fields, the capital quantum operators, vacuum. So let's just do this calculation, 0. Then I need to write AK dagger, which is just going to be beta k AK plus alpha k star AK dagger. Then the quantum operator A, alpha k AK plus beta k star AK dagger, acting on the vacuum. So you see, I'm using the time-dependent annihilation creation operators to count how many particles there are around. Now notice that this, when it acts on the vacuum, gives me 0 because of the property of the vacuum. So this term gives me 0. And if I dagger this term, I also know that when I act with a dagger from the right there, I also get 0. So this term is also 0. And now what I see that this is just a number, this is just a number. So I can just take them out of the expectation value. And this is beta absolute value square, 0, AK dagger, 0. Now, how do I proceed with this? This is equal beta k square, 0, AK dagger, minus AK dagger, AK, 0. Notice that I subtracted 0. Because what is the difference between this line and this line is just this term here. This term is 0 because A acting on the vacuum is 0. So why did I bother to subtract this term? Because now I have the commutator. This is beta k squared commutator of AK dagger. This is equal beta k squared delta 3 of k minus k 0, 0. This is equal beta k squared. This is the momentum delta function of 0, which is the volume, right? It has the dimension of a volume. It is a volume. And finally, this is 1, right? Because the vacuum is normalized to have a norm 1. So what I learned after this long calculation, the total number of particles is equal beta squared times the volume. So what I learned, beta squared is the number density. So this is really beautiful interpretation. Notice that we started with beta is equal 0. And by using the Hamiltonian, we define the counting operator. And we understand the beta squared is the number of particles at the time t divided by the volume. Therefore, beta squared is a number density. Is there any questions now? Okay, let's proceed. Let's proceed. So now, essentially, I can just write down on the board everything that is needed to do this type of calculations. It's really beautiful because we have the physical interpretation and we also have a closed system of equations. So we have the omega squared is equal k squared plus m squared of t. So let me just do this, right? This is the time-dependent frequency. We start from initial condition alpha in is equal 0, alpha in is equal 1, beta in is equal 0. We solve the system of differential equations, and then we know that the number density is beta absolute value squared. So everything I write here is all we need to do these calculations either on a computer or analytically. Initial condition, system of equation, physical interpretation as occupation number. Now, let us remember that I want to also understand one subtlety, which is omega, concretely for our problem, was k squared plus g squared phi tilde square minus a dot dot over a square root. And I see that there is time dependence due to this term, and there is also time dependence due to this term. But remember, phi tilde is a phi. And also remember that with this dot, I'm taking the conformal time derivative. So actually, d in d tau, because this dot really means d in d tau in this discussion, this is equal scale factor d in dt. So when I have the term a dot dot over a, parametrically, this is a square h square. Because each time I have a derivative with respect to conformal time, I have a power of the scale factor. So actually, this number depends exactly on what type of expansion you have, but that's what you have parametrically. And then you can see that in the early universe, as a tends to 0, these terms tend to 0. So what it means at early times, these terms are exponentially small. So what it means that omega is essentially constant. So we can do a good quantization. That's what allows me to take alpha initial is equal 1. Because if I say alpha initial is equal 1, I'm telling you I'm starting from no population, as if it was in Minkowski spacetime. And in fact, this is true because the time dependence part is exponentially small at early times. And remember the analogy of the pendulum if I change the length slowly. If I change the length slowly, there is no excitation produced. So at the beginning, if this is interpreted as the length of the pendulum, these are exponentially small functions. I'm changing the pendulum very, very slowly, nothing really happens. But then later on, they can become important. In fact, just by looking at the nature of equation, you see that there is production when this combination here is more important than this combination here. Notice that omega has dimension of an energy, In natural units, omega dot as dimension of energy squared, because taking time derivative adds one dimension of mass. So the condition for efficient production, let's say strong production, is when omega dot is greater than omega squared. On the other way, if omega dot is much smaller than omega squared, here is adiabatic variation. So when this happens, there is a very negligible particle production. Instead, when this happens, there is a strong particle production. So we are really be able to be quantitative. Let me now show how this applies to our problem. So in this problem, we see something even more interesting than that. Here, it is neglected the expansion of the universe, because when you do during reheating, essentially, the fact that the universe is expanding doesn't really create quanta, but the oscillations of the inflaton field create quanta. And here you see that there is a phenomenon of resonance, because imagine you have a pendulum, and you change the length of the pendulum in a periodic way. Then the length of the pendulum, there is going to be some resonance bands where you can exponentially create more and more quanta. And here is exactly what you see. You can rewrite the equation in this way. By writing the equation in this way, essentially, you learn that the parameter that controls the production is this ratio here. This is what I was telling you yesterday, that if Q is of order 1 or bigger than 1, you have strong production. And phi 0 usually could be as big as 10 to the 18 GeV. This is of the order of 10 to the 13 GeV. So this term is really big. And you could also take G to be 10 to the minus 2 or 10 to the minus 3 and still have a Q of order 1. So you can have an efficient particle production even if G is as small as 10 to the minus 2 or 10 to the minus 3. Now, this is a diagram that indicates the resonance bands. In a sense, here you can see that the amplitude is growing. And here, by doing the calculation of the occupation number in the way we did it on the board, we see that there is a growing of the occupation number. Notice, and I'm going to discuss this in a moment, that the occupation number grows only at some instance. Then you see it grows, then it stays constant. It grows, it stays constant. It grows and it stays constant. It grows periodically. And notice that it's an exponential growth, because here I'm showing the logarithm of the occupation number. By taking the average growth, is essentially something, the solution looks like this. It's exponentially growing, and mu is called the Floquet parameter, doesn't really matter. It parameterizes the exponential growth. For some given values of Q, you are on the growth. For some other, you are not on the growth, essentially. And that's essentially all I want to say for this. And let me also say, you see, there is the presence of resonance band. Here is what happens when you include the expansion of the universe. This calculation was done without expansion of the universe. The field chi will keep growing, because if a mod is in a resonance band, it will remain in the resonance band forever. Here is the equation where there is the mod accounting for the expansion of the universe. The expansion of the universe changes the physical momentum of the mod, because what is entering in the equation is no longer k, but k divided by a. And it also changes the amplitude of the inflaton field. Remember, we saw these 2 lectures ago. The amplitude of the inflaton field decreases because the universe is expanding. Therefore, the driving term, which is proportional to the amplitude of the inflaton field, will eventually slow down, and eventually the amplitude of phi is too small, and you no longer have production. So we expect that at some point this production stops. Moreover, a mode sometimes in the resonance band and sometimes is not in the resonance band. So for example, here you see now here we have order hundreds oscillations of the inflaton field. Sometimes the mode is growing because in the resonance band. Then sometimes it's not growing because it's not in the resonance band. Then here is in the resonance bands again. And then eventually stops growing because the amplitude of the inflaton field has become too small. Is there any questions? Okay. if there is no question, let me show you how I can even be more explicit than that. Now it's going to be 10 minutes of rather detailed calculation. For those of you who are interested, I want to show how we can even be algebraically doing these solutions, in a sense, in a way that is extremely simple. Well, not extremely simple. It leads to extremely simple results. I thought the calculation is going to be a little complicated. I want to also explain why the occupation number was growing stepwise. If you remember the slide that we saw before, there was an exponentially growing occupation number, but the occupation number was not growing at all times. It was growing, then it remained constant. Then it was growing, then it remained constant, so on and so forth. And the reason for that is immediately understood when we write the mass, the time-dependent mass. Remember, now we are doing Minkowski space-time. We are forgetting about the expansion of the universe. So we take omega k is equal k squared plus g squared, phi 0 squared, sine square of mt. So we are taking the scale factor equal to 1. So we are in this calculation here, in this discussion, we are neglecting the expansion of the universe. Notice that the production takes place when omega dot is greater or equal than omega squared. And remember that here I have a function that is the sine function. And I ask myself, where is the moment where I have most of the production? The moment in which you have most of the production is when the sine function varies the most. The sine function varies the most when it crosses 0. Moreover, the moment in which the sine function crosses 0, this term is also 0, right? So you see, this is the moment in which omega dot divided by omega squared is greatest. And that's why, when we look at the particle production, if here is log of nk as a function of time, we have something like this. The particle production grows each time I cross 0. So each time the inflaton crosses 0, there is a pump in the energy of the field chi. Whenever inflaton crosses 0, the field chi gets produced. So we understand that in order to solve this problem, mathematically, we can study the equations of motion near to the zeros of the inflaton field. For example, I'm interested in the first episode of particle production. To study the first episode of the particle production, I only study the behavior of the system when the inflaton field is close to 0. And in particular, it is, in order to simplify my equation, I'm going to linearize the evolution of the inflaton field. I'm going to pretend that the inflaton field evolves in this way. By pretending that the inflaton field evolves in this way, I will be able to solve the system analytically, and I will also be able to reproduce the precise amount of growth, because notice that the growth takes place only for a very narrow interval of times across the zeros of the inflaton field. So that's what I'm going to do. I'm going to approximate the evolution of the inflaton instead of being sine, just a linear growth. This is the pleasant thing that I can then solve the equations analytically, although the solution is still not simple, but I can still solve it. And secondly, I can still reproduce the exact calculation, because notice that the production only takes place near the zeros of the inflaton field. So in particular, I'm not going to maybe do all the details, but let me just try to explain. Here, I'm going to maybe be a bit quick. Let me see how much I managed to do. We are going to essentially expand phi 0 sine of mt. I approximate it as phi 0 mt. This is the approximation that I was pictorially drawing here. So the inflaton is approximated as a linear evolving function. Also, I'm going to rescale. Now the time, I'm going to choose it in this way. This is just because with this rescaling, the equations of motion simplify a lot. And the momentum, I'm also going to rescale it in this way. G m phi 0. If I do this approximation and this rescaling, the equation of motion for the mode function chi becomes as simple as this. Notice that the sine square of the inflaton now has become tau square because I have linearized the inflaton field. And this is a differential equation that we know how to solve exactly. The solution is written in terms of parabolic cylinder functions, which I'm not even, well, I'm going to just discuss some properties. So this is a second order differential equation. So there are two integration constants. And there is this function d to the minus a half minus I p square over 2, 1 plus I tau, right? The mode functions in general are complex. And then there is the second mode, which is another parabolic. So just to summarize, we notice from the plot and also from the discussion of omega dot divided by omega square that the production takes place only when the inflaton crosses 0. Therefore, for the purpose of simplifying my life, I approximate the evolution of the inflaton as it was always a straight line. If I do so, and if I do some rescaling, the equation of motion acquires this form. And moreover, this equation of motion can be solved exactly in terms of these functions here, which are called parabolic cylinder functions. Now, what do I learn from this solution, right? That's what I need to understand now. Well, in order to understand things from this solution, I'm gonna study the limit of the parabolic cylinder functions at very early times or at very late times. And in particular, I can verify that there is this limit here, lim for tau that goes to infinity of the first parabolic cylinder function this is equal a constant times e to the minus I tau squared divided by 2 plus p squared divided by 2 log tau divided by tau to the half. Written like this is not very illuminating, but in a moment, hopefully, it will be illuminating. So what I'll say, right, this is the general solution of the equation of motion. In order to gain some insight, I'm going to expand these terms at asymptotically early times or asymptotically late times. And for example, when I take the first one, just you look on the mathematical books, right? They have the properties of the special functions. I'm going to find that the parabolic cylinder function in the first term is going to satisfy this behavior here at very late times, when tau goes to plus infinity. Now, if I just look at this, I'm saying, okay, so what, right? But let me also study this limit of e to the minus I omega d tau divided by square root of 2 omega. If I study this limit, this becomes e to the minus I p squared plus tau squared, right? This is how omega rewrites in these new variables, divided by tau squared plus p squared to the half. And now let me remember that I am at asymptotically large times. If I am at asymptotically large times, tau is much greater than p. So this I can simplify it away. And here I can do a Taylor expansion in the limit in which tau is much greater than p. So let me do a Taylor expansion of the integrand. So what I will have e to the minus I tau plus p squared over 2 tau in d tau divided by tau to the half. But then I notice that this term here is exactly this. Right, because, so let me repeat, right? This is my solution, it's true at all times. If I take the limit of very large time, my solution will look like this, the first term. And then what I notice that if I do this calculation, and I just do the expansion at very large time, that's what I'm gonna get. And you see the integral of this term is giving me this term, and the integral of this term is precisely giving me this term. So what I notice that this function here, at very early times, it becomes e to the minus I omega d tau divided by square root of 2 omega. And I can also verify that this solution here becomes e to the I omega d tau divided by square root of 2 omega. So asymptotically late times, they become something very simple. And now I remember that in the omega constant case, I had that, so if omega was equal constant, I had that alpha was equal e to the minus I omega t divided by 2 omega, and beta was equal e to the I omega t divided by 2 omega square root. So what I see that in my solution at asymptotically large times, I am recovering a form of the solution that applies when omega is constant. So in a sense, if I take this solution and I evaluate it at time is equal minus infinite, I get the coefficients alpha and beta before the particle production. And if I evaluate it at late times, I'm getting the alpha and beta coefficients after the particle production. So pictorially, I know that this is the occupation number. That's what we saw before. It was doing like this, then it grew. Each time it grows. And in order to study the growth of the occupation number here, I have some value alpha in and beta in. And here I have some values of alpha out and beta out. And as you can see that apart from time is equal 0, alpha is behaving as if omega was constant, because in this regime, omega dot is much smaller than omega squared, and also in this regime, omega dot is much smaller than omega squared. So I have solutions where it's like if omega was constant, solution which is like if omega was constant, and then there is a non-trivial change of alpha and beta only in this region here. My solution precisely indicates the little change, because these functions here, at very early times, they give me the value of alpha in and beta in. And the same solution at late times, they give me the value of alpha out and beta out. And so by just looking at the exact solution, I can learn mathematically how alpha in, beta in will give me alpha out and beta out. This problem is completely analogous to the problem of scattering. Remember, right, when you solve in quantum mechanics a problem of scattering, you will have essentially a potential well, for example, and you will have a state which is the ingoing and the outgoing. And here is completely equivalent to having alpha in and beta in. Then there is a scattering potential, and then you have alpha out and beta out. In the problem of quantum mechanics, the variable is x, right? So you have one mode proportional to the e to the minus ikx, away from the scattering region, and a problem e to the ikx. So this would be something like e to the minus ikx, e to the ikx, and the same is true here, e to the minus ikx, and e to the ikx. In the case of scattering, we would have a special variable, right? And that's the scattering takes place in that direction. Now there is omega t, e to the minus I omega t, omega t, omega t, omega t. And by taking the exact solution, we know how to relate the Bogoliubov coefficients before the scattering to the Bogoliubov coefficients after the scattering. Scattering means value of the inflaton field crossing 0. This is complicated. I know this part is a bit complicated. I can point you out to papers where everything is done in very slow detail. But let me ask you if you have any question right now. Okay, so everyone got, all of you got everything. I'm very happy. And let me just write down one form. Essentially, when you do scattering, you can relate these things in a matrix form. You can write the coefficients after the scattering as a matrix times the coefficients before the scattering. So something like this, alpha out, beta out, is equal a 2 by 2 matrix times alpha in, beta in. The knowledge of the exact solution across the scattering region will allow me to get the final coefficients in terms of the initial coefficients. For the problem at hand, this matrix is very complicated, but let me write a piece of this matrix, which is the only one that we need. E to the minus pi p squared divided by 2, e to the minus pi p squared divided by 2, 1 plus e to the minus pi p squared, up to phases, up to complex phases. In fact, when you do the full calculation, this will look much more complicated because there will be some complex phases complicating the discussion. But for our purposes, that's all I want to visualize. So once again, right, maybe we can forget about the mathematical details, but let me at least tell you what I have done in a pictorial way again. I have that the inflaton is crossing 0 only on a discrete number of points. As a consequence, the number density is growing each time the inflaton crosses 0. So each time the inflaton crosses 0, we saw that the number density was growing because this is the only moment where omega square is greater than omega dot is greater than omega square. Only when the inflaton crosses 0. So particle production takes place at this moment. Boing, boing, boing. Right? So it doesn't go continuously. And as you can see here, particle production takes place each moment the inflaton crosses 0. We mapped mathematically this problem to a scattering problem, where you have a particle that doesn't do anything, then there is a scattering barrier, and then the wave function changes. What are the coefficients of the wave function in our mathematical problem? The Bogoliubov coefficients before and afterwards. So you can, each time you have a scattering, you can apply this matrix here. This matrix here is complicated, but people worked it out fully. So there's no more need to solve differential equation. You just apply this matrix continuously each time you have a scattering. Each time the inflaton crosses 0. So if you want to see what is the particle production in this interval here, you see the inflaton crosses 0 3 times. So you start from your initial state, 1, 0, and you apply this matrix 3 times, and you will have the particle production after 3 times. There's no more need to solve differential equation. The problem has been worked out, like if you had 3 successive scatterings. And in particular, at the first scattering, we take this matrix, right? At the first time, so the first production, we start from alpha in, beta in is equal 1, 0. So that's what we're going to plug here. We apply this, and we see that this is the only element that really matters. No, but it's the same. This is the only element because it's acting on the element 1, 0. And so we learn that the particle production after the first scattering is e to the minus pi p squared. And if you go back to the original variables, this is e to the minus pi k squared divided by g m0 m phi 0. So you see how nice, simple mathematical form there is by just doing this very complicated problem. The first time you have particle production, you know that this is going to be the spectrum, right? The k-dependence part. Notice that there is this very non-perturbative production here. Notice is e to the minus something divided by g. This is the coupling constant, right? When you have something like this, it's clear that this is non-perturbative because you cannot expand this in the limit of small g. So this phenomenon here is clearly non-perturbative. Let me just show you, just to show you how good this method is, let me just show you one example. This was done for a system of fermions. It's not for scalar field, but the concepts are completely the same. And in red, there is the result applying this scattering method after 7 instances of particle production. And in green is the full numerical result. On the x-axis, there is the momentum of the mode. On the vertical axis, there is the occupation number. Since this is a fermion field, the occupation number is never greater than 1. Here, it's a fermion, and there were 7 times of particle production. The inflaton crosses 0 7 times. And you can see in green is the numerical result, and in red is the result obtained with this scattering method that I just reviewed with you. And you see that the result is almost perfect, right? So you see that doing these scattering methods provides incredibly good results. Okay, let me ask you if you have questions. Yes, there's a question. Yes?
Yes, so I will read the question for you. As T grows, I guess the number density is not completely constant because each step, but slowly decreasing due to cosmic. No, sorry. Is not completely constant between each step, but slowly decreasing due to the cosmic expansion.
Absolutely correct. Perfectly correct what you say. So this scattering matrix each time varies a little bit because there is the expansion of the universe. So you can use this method in Minkowski, or you can use it for expanding universe. And if you use it for expanding universe, it's precisely what you said. This matrix here becomes less and less powerful in a sense because the amplitude of the inflaton field is slowly decreasing. So what you say is perfectly correct. How much time do I have? 10 minutes? Okay, I'll try to finish in 10 minutes for sure, because I just want to discuss what's going on afterwards. So let me just find what I want to say. And remember where now we saw the movie, right? And there was the initial moment that the field chi was growing, and then the field chi was inhomogeneous, and then the field chi goes against the inflaton field, and it makes the inflaton inhomogeneous as well, right? You cannot imagine in your mind, right, that you create the field chi, which is going to be completely inhomogeneous, and instead the inflaton remains homogeneous. This is not physical, right? Because the same interaction that has produced the field chi, this g square, phi square, chi square, you will have also the field chi that goes against the zero mode. You can imagine the inflaton as a condensate that has particle with zero momenta, and then the field chi goes against the inflaton field, and the inflaton field also gets fragmented. You remember in the simulation we saw this fragmentation. The calculation that we did now on the board does not account for this fragmentation because the calculation that we did had a homogeneous value of phi, right? Always we say phi is only function of time. Therefore, the calculation we did only accounts from the early stage of the phenomenon until the field phi gets also fragmented by the interaction with the inflaton chi. And this rescattering, so this phenomenon I just discussed, this fragments the inflaton. So chi, phi of t produces chi, and then chi fragments the inflaton field. The inflaton field acquires just this fragmented distribution. This destroys the coherences. And stops preheating, essentially. But then we ask ourselves, what are we left with, right? So preheating stops because there is going to be this coherency is lost. And then what are we left with? In general, reheating finishes when you have a thermal state. So the question we ask ourselves is, do we get a thermal state or not? And the answer is absolutely not. So the distributions formed, we're going to see them in a moment. The distribution formed have rho total much greater than the typical energy of one excitation to the fourth. Remember, dimensionally, rho is an energy density. So energy density is energy over volume. In natural units, it has dimension of energy to the 4. So to see whether you have something thermal or not, a good way is to compare the the energy density with the typical energy of one excitation. If you have a thermal bath, Rho is proportional temperature to the fourth, and the energy of one excitation is proportional to T. So for a thermal bath, this would be an equality, right, for a thermal bath. But in our case, the Rho is much greater than the energy of one excitation. So what it means that with respect to a thermal distribution, we are very much populated in infrared. We have a lot of particles with relatively low energy. So thermalization will need to go through particle fusion. The problem is that in this model that we discussed, there is no really big efficient fusion channel. You're going to have to put two vertices. Remember, our vertex was G squared, phi squared, chi squared. So what we will have processes, for example, that they combine two vertices, where you have 4 particles going in and 2 particles going out. So you see, what is the net balance of this process? You decrease the number of particles and you increase the average energy of this particle, right? Because you have 4 particles that become 2 particles. By conservation of energy, these have more energy than the incoming state on average, right? So what it means that this distribution will try to go in the UV. Now let me just show you the slides which are obtained from Lattice Simulations, and then I'm going to stop. So here are again the result of these Lattice simulations. Now you see these preheating, the linear phase, the one that we could do analytically, was up to MT of order of 30, 40, something like that. But now you see that we are plotting this for much longer values of time. And here we are plotting the energy density in the various components. But what we learn by just looking at these plots is going to be very detailed. I'm going to just tell you the result, is that the typical energy of each quanta is of the order of a few times the inflaton mass. But then by conservation of energy, you see all the initial energy of the inflaton has gone into this populated state. The initial energy of the inflaton was this quantity here. But remember that for the inflaton, the amplitude is much greater than the mass. So the energy is a typical values of the mass, but this total energy is many orders of magnitude greater than the mass. So remember, the number density is about 10 to the 9 more than the typical energy of each quanta, in a sense. And that's what's going on. Here, I'm going to show with you the time evolution of the spectra of the field chi, that's the one that we see on the right, and of the inflaton field, that is one that we see on the left. Horizontal axis is the value of the momentum. Vertical axis is the occupation number. Now we see that initially the field chi is the first one to be produced. Because you see here, the color red, green, the field chi grows earlier than the field phi, as you can see from here. And as you can see that initially the infrared part of the spectrum gets excited. But then if you look at late times, compare the purple line and the blue line, you see that the population tries to go in the UV. This is the phenomenon of particle fusion that I was telling you about. But this phenomenon is very slow, and we cannot do it with the lattice, because the state that you see here is still very far from thermal. And there is no way from lattice simulation that we can really go. We see that the state is going towards thermal state, but it's still very far from it. Finally, I was telling you that we don't know what the equation of state of reheating is. And here from the simulations, we find that in this intermediate stage that I'm discussing with the simulation, the equation of state is neither the one of matter nor the one of radiation. Remember, for matter, we have W is equal 0. For radiation, W is equal 1/3, so 0.3333. And here you see that we have a moment in which the equation of state is neither matter nor radiation. Because in a sense, we have a very messy system where there are inflaton quanta that are massive, and then there are the quanta of the field chi that by themselves would be massless, but they are coupled together. So the system is really a very complicated system. And that's essentially all I'm about to say for today. Let me just make one comment and then I'm done. So today we saw the phenomenon of non-perturbative particle production at reheating. And this is a very complicated system. And we just saw the calculation for a toy model, right, where there is just two scalar fields, and you saw how complicated it is. So now try to imagine if you want to put fermions, gauge fields. This is going to be much more complicated. Features that we described here will follow, but in a more complicated way. The end result is going to be a thermal spectrum, but our tools for simulations only account for the early stages. And this essentially concludes what I want to say about reheating. And tomorrow, in the last lecture, we are going to apply similar calculation techniques for particle production during inflation. So imagine that there is a model where there is, I'm going to discuss tomorrow the model, this non-perturbative production, not at reheating, but already during inflation. Of course, we don't extract all the energy of the inflaton, otherwise there would be no more inflation. But it's enough to extract a little bit of energy to the inflaton to get some interesting phenomenology. So the mathematics will be somewhat similar, but the physical applications will be very different, and this will be the last lecture of tomorrow. Okay, thank you very much for your attention. Let me ask you if you have questions.
I don't see any question in the chat.
Okay, so
we can stop here, and let me remind you the schedule for the last day of the school. Tomorrow we'll start at 2:30 p.m. with the first lecture, and then the second lecture will be at 4:30 p.m. So both lectures will be shifted by 1 hour, and the discussion session will be right after the last lecture. So the time of the discussion session will not change. Okay, see you tomorrow. Bye-bye.
Bye.